Good morning. We will continue our discussion of sprays as multiphase flows. Towards the end of last class, we had derived a co-moving derivative in a slightly general formulation involving not just advection through a spatial coordinate x1, x2, spatial coordinates x1, x2, x3, but also through a velocity coordinate v1, v2, v3. And we said F1, F2, F3 would have to be the force vector per unit mass for this advection through the velocity coordinate. The simplest of such force vector that you can think of, let us say, is gravitational force. So, I have an ensemble of particles that are sitting with no interaction, and let us say they are just remaining at rest, and F1 and F3 are 0 and F3 is some minus g. So, that would cause particles that were at rest at some time t equal to 0 to begin to accelerate and acquire a velocity. And if I was to study this in the context of a probability density function of these particles, it would be where the initial velocity v0, which in this particular example is 0, would have become some v1 at some later point in time, following the rule that v1 is v0 plus a dt, a in this case being minus g. So, the advection through the velocity coordinate happens due to an external force, not due to forces that may originate due to interaction between these particles. So, let us be clear about what F1, F2, F3 are. I will mark this in red. This is the external force per unit mass or acting on the ensemble of particles, on this population of particles. If I look at what happens due to the interaction between the particles. So, we started to look at another example. Between a pair of particles. So, let us say I take a particle of some mass m and another particle of some mass m, and my system now is this two particle system, and if I allow these two particles to come collide inelastically, the momentum is destroyed due to these forces that may originate at the point of collision, and all the kinetic energy in these two particles is converted to heat. That is our classical mechanics understanding of this kind of a collision. Now, when I look at this in the probability density space, I have one Dirac delta function at plus v. This is actually half a Dirac delta function, because the sum total f dv going minus infinity to infinity, if I am only looking at one velocity coordinate, then f dv would have to equal 1. So, this would be half a Dirac delta function at v, I will call this v0 just to distinguish it from the coordinate v, and this would be half v minus minus v0. If I was to define f to be the summation of these two, that would ensure that the probability density function integrates out over its appropriate limits to 1. So, when this collision happens, this probability density function, which I have indicated in black, becomes one probability density function given by delta v minus 0. The sum total area under the distribution of course remains the same, but it has advected from this 2 peak probability density function towards this 1 peak at 0. What is the cause of this advection? If I go back to the formulation I had for the total derivative, none of these terms can be responsible for this, because it was entirely an internal force. So, essentially this total derivative of f has an effect due to collisions and any other systemic effects. So, if I rewrite the system equivalent of this, it has to equal some contributions due to collisions plus any contributions due to changes at the system level. That is, if I had an ensemble of droplets that were, let us say, of total mass m, if I was to draw a system boundary, and by definition a system boundary is where you do not allow mass transfer across it, what sort of effects can cause the system mass to go up if I do not allow mass transfer across the system boundary? One such effect is if I have a nucleation of droplets inside due to some condensation process. So, I had some vapor inside and the vapor condensed to give me a droplet. So, now as far as the droplet phase is concerned, there is an increase in the mass due to this nucleation and condensation process. So, I could have some droplet generation. Okay, I say generation, but it could also mean destruction due to evaporation. So, these are all the effects that can happen at the system level. These are all the reasons by which the probability density function of this droplets in the size velocity space can move, can change. So, if I combine the system level equation with the version we had before from the advection form, we find, and I will write it in a slightly compact fashion. This is in the spray literature. This is called the Williams spray equation due to a man named Foreman Williams. And we must also mention that this is very similar, in fact has a very strong connection to the Boltzmann equation that physicists use to study gases. So, you can think of gases which is made of molecules, which are made of molecules and we can write a probability density function for the ensemble of particles. Let us not go, I mean, for an ensemble of particles in the size velocity space, and that advects through the velocity coordinate, size coordinate due to respective forces, and is altered due to the collision term. So, this this also has connections to the Boltzmann equation, which is used in kinetic theory. So, now we started to define this f as being our probability density function, and we now have an equation that tells us how f changes in the spray. If I go back to what f is for a moment, we said f is a probability density function. We did not quite precisely define if it was number probability density or mass probability density. We can define f to be either of the two, and it would work just as well. Nothing in the equation would be different if you make this a mass probability density function as opposed to a number probability density function. Okay. Now, if you look at this as the mass probability density function, so I am now going to define f of r. Of course, I forgot to write my r term, so let me include that. So, I will describe what each is. This is basically due to growth of droplets, this is due to collisions, this is due to birth of droplets or death, this is the advection in the velocity coordinate. The explicit time rate of change. So, if I now continue on and look at what the forms, if I define f as a mass probability density function, and I will use a vector notation just to so, this has, just to be clear, it has units of kilograms per micrometer of the drop size, per meter of physical space, per meter per second of velocity. So, this is the units of this probability density function. If I integrate this over the appropriate limits of R, let us say. So, I will take this equation. So, F is a probability density, and I will just quickly write out the integral condition that we have in an explicit form. That is the probability of finding a drop in the size 0 to infinity with velocity component. So, really this first integral is a triple integral. At a given point, the probability of finding a drop from 0 to infinity and components minus infinity to infinity is 1. Now, this is a little different from the form that I developed earlier, that I have written down here, where the normalization factor for this probability is the total ensemble of drops in the volume x to x plus dx. Okay. So, in other words, the if I take the normalization factor as being the total set of drops in the entire spray, then I have a probability of finding a drop in my volume x to x plus dx. So, probability of finding any drop in my volume x to x plus dx itself being less than 1. So, if my normalization condition is the total set of drops in the entire spray, then the probability of finding any drop in the volume x to x plus dx is some number less than 1. Of that count, this integral minus infinity to plus infinity and 0 to infinity of f dr dv is a smaller, this is the total number of drops found at that point in the volume x to x plus dx. So, really speaking, this is normalized to the mass of drops to the volume x to x plus dx. So, if I take the normalization, the denominator in my normalization condition as being the total mass of drops in the volume x to x plus dx, then that is how you get this integral to be 1. In fact, this is the total mass of drops. Okay. So, the units on this f are not the same as the units that I have written here. You would not have this per meter. Sorry. That per meter is a probability density function in the spatial coordinate. So, if I want to ask the question, I have a spray, I want to ask the question, what is the distribution of droplets in this spray? I do not care what their size is, I do not care what their velocity is, how is the mass distributed in this spray, okay, which is f is a mass PDF. If I ask the question how is the mass distributed, I may find that there is more mass here in the edges and that there is less mass somewhere here in the middle, let us say. So, in a contour sense, I might say there is a contour inside which there is low mass density, outside which there is high mass density. Okay, so, this is a spatial mass PDF. If I take this spatial mass PDF and if I take a small point and I look at what the spatial mass, what the distribution is within the mass that is concentrated at this point. So, I am now not concerned that there is less mass here, but if I said if I took the mass concentrated at this point and I want to see how is this mass distributed in the size and velocity coordinates, I can create a PDF and that PDF is given by this integral. Okay. So, if I now say, so this mass PDF is defined point wise. So, the difference is if I treat x as a PDF variable, that is as a variable in which I am also accounting for the probability density, then I get this per meter, and per meter actually is if I am only dealing with one spatial dimension, but per meter cubed if I am dealing with 3 spatial dimensions. Just like this would be per meter per second if I am only dealing with 1 dimensions. So, this is for a 1D case, this is the units are this. If I am not dealing with space, with the spatial coordinate explicitly as being part of my PDF, that is I am not interested in how this PDF, how the mass is distributed, a probability density of mass distribution spatially, but I will treat space just like time and take a snapshot. So, this is how we did our earlier discussion. So, if f is a function of r and v with x and t as parameters. Okay. So, if this is the case, then only r and v are my parameters, whereas if this is the case, then I have another integral, another triple integral minus infinity to infinity of dx. If I have to normalize, if x is also part of my PDF independent variable list, then this is the condition that I have to satisfy, and this will also be a triple integral. On the other hand, if I want to treat x as only a parameter, so at every point I create a PDF of only size and velocity. This is how, let us say we do our PDPA data set. We are not doing a PDPA data set treating x as one of the independent variable list in the PDF, because PDPA by definition is a point measurement instrument, whereas if I am looking at something that measures spatially, I may be able to do the x, I may be able to find x as part of my independent variable list. Okay, so, if I now write an evolution equation for this f, or not evolution equation, as a normalization condition for this f, then and this is true at every point. Again, this is a triple integral. If I now continue, if I take my Williams-Spray equation, I am going to take the case of a dilute spray with no evaporation condensation. So, the SC and ST are 0, and this is what we call a dilute spray. Dilute non evaporating spray. Dilute essentially means no chance of collisions happening. So, the collisions are so rare in occurrence that I can ignore that effect. Okay. So, if I set this to be equal to 0 on the right hand side and perform this integration over the size coordinate. So, I want to now see if I only integrate this equation in the r coordinate, we saw from our discussion of multivariate probability densities that this will also be a probability density in only the velocity coordinate, because whatever this function is a function of only the velocity v, and that in its that will also be a probability density, because the integral of that over the appropriate limits of velocity would become 1. We saw that in an example earlier. Notice how in some instances I brought the integral inside the integration, and in other instances I did not. The reason for this is just to understand that in this case the integration over r and time derivation are commuted. So, I can exchange the two operations in order. So, if I now define this as being some sort of a probability density function in velocity, correct. So, since we said this will have all the status of a probability density function, we are able to do this. So, if I rewrite this, what do I get? sorry, this goes 0 to infinity. Notice how I have still left with some f terms. I do not have an equation only in g terms, because I know integral 0 to infinity, let us say. I have replaced integral 0 to infinity f dr with some g of v. Okay, it is like a probability density function in the velocity coordinate, and I am able to take care of the first two terms, but the last two still have this f part remaining in it. Okay. If you look at especially the third term, there I still have f, because if f j, the force acting on a set of particles, external force, is a function of r, then if it is not a function of r, I can take that out and write this as f j times g. So, if f j is not a function of r, I can write this as f j times g. If it is a function of r, then I am in trouble, because I have f j from my earlier formulation as the external force per unit mass acting on these particles, and if there is an size dependence on it, then this becomes a little tricky to write. If we think of an external force per unit mass on a set of droplets where there is size dependence, the simplest of such forces is drag. When you write the drag on a sphere, for example, the drag on a sphere scales as the size of the sphere. So, you essentially have to have, so this is not something that is out of the ordinary, it is very commonly found in sprays, that this f j is a function of r, and as a result I am not able to do this integration right away. This is the start of what is often called the closure problem. So, this part, say for example, I will set r dot to 0, we will come back look at that later, but this part here where I am unable to write f j, this integral f j f dr in terms of g, is what is the reason for what we call our closure problem. Okay. So, what we will do in the next class is we will start from here, and the governing equations that we are used to seeing are our Navier-Stokes equations. So, we want to see how to go from something that looks like the Boltzmann equation, or in this case our Williams-Spray equation, and arrive at a multi-phase or even a two-phase set of equations, two sets of equations describing the gas phase and the droplet phase. So, we are going to do that mathematics in the next class, but before that we want to understand what is a phase. So, if I take a spray, we have done this many times, we have air in the interstitial space between drops, but if I take all the drops with vacuum in between and the air alone, in some sense they look alike, in the sense that drops are macroscopic distinct entities that are separated by emptiness, in the case that I talked about where the drops are taken out with vacuum in the middle. Now, if I really zoom into the air part, the air is also discrete molecules with emptiness in the middle. So, really the only difference between air and the drop phase is the size of the particles, where molecules of oxygen or nitrogen may be a few tens of angstroms, drops of liquid may be fractions of a micron to several hundreds of micrometers, and the interstitial space also scales. But other than these scaling effects, the nature or morphology is somewhat similar. We will use this argument as our building block to replace the drops with a continuum, just as we replaced a set of discrete oxygen molecules and nitrogen molecules with this continuum idea called air. We will replace a set of drops with a continuum called, we will for today call it a spray, or call it a drop fluid. So, this drop fluid plus air together, put together, makes our spray. We will see how to get this far from the Williams spray equation in the next class.